All right, hello everyone. Today is July 7th. We are going to continue on with our chapter 12 homework. We last completed chapter 12 homework problem number 9, so we'll go on to problem number 10. So it says that we have this compound right here. We had H2 under platinum. We're going to get rid of that double bond, and we're going to form the alcohol.
For some reason, when I'm drawing that, it won't let me put the OH. So then it only lets me put the O, and then it says that it's wrong.
All right, so let's go to question 11. Question 11 has sodium borohydride. That's a good source of a hydrogen. It says adds curved arrows for the first step. So let's do the first step. So we have this compound. They want you to draw this. They want you to draw the full boron structure. So we'll do that. Negative sodium plus here. The hydrogen is going to come in here like this. It's going to release some electrons from the double bond. Then we'll go to step 2. Step 2 is not going to be a proton transfer. It's going to be a deuterium transfer because we have D2O. So we are going to add. So let's go to step 2. It'd usually be a proton transfer, but in this case, it's going to be a deuterium transfer. And everyone should know the difference between deuterium and hydrogen. It's just deuterium has 1 neutron, hydrogen has 0 neutrons. So there's some questions in the chat. All right, thank you, Stephen, for answering that question. This homework takes a little bit of getting used to as far as the achieve goes, so please get used to it as quick as you can. This is how we're going to take all our exams. So the difference between a deuterium and a proton is a proton has no neutrons, a deuterium has 1 neutron. So we'll do this, we'll do this. And it says draw the final product. So our step 3 will be here. I have one and a half more weeks of my own class. So, I'm really happy to get that done. That way I can move on to, my research paper that I was working on. So it's just been more difficult, I'll say, to do that. So for step 3, this is a D, this is not an O. I'm gonna draw that a little better for you. That's a D. D is in delta. So that's step 3. So if you do all that, you should get 100% on that question. I might draw question 12 on the same slide. Question 12, there's not much to it. It's just a hydride acting as a nucleophile, then followed by a proton transfer. So like I said, for 12, there's not a lot to this. You have a hydride, lithium aluminum hydride is a good source of a hydride. So it's a nucleophilic attack, and then followed by proton transfer. I had my volume down at 2. So if you were asking me any questions, maybe that's why I wasn't hearing. I turned the volume now up to 100. So this will yield the alcohol. Let me see. Let me see something here. I see what they want you to do is add another. So there'll be another. Let me see this. I put this up here. I'm gonna take my time with this. This won't be the final answer. I'm thinking this through. I'll put that hydrogen here. If this pronates itself again, that'll be good. So this will be your final answer right here. So that's 11 and 12. Let's go on to 13. So 13 says predict the oxidation product of treating the given alkene with the reagents shown. Only draw one enantiomer. If more than one is possible, include protons. Note that MCPBA is metachloroperioxybenzoic acid. That's what we're going to be talking about today. So basically what's going to happen, I'm not going to draw the whole structure. You're going to form an epoxide, and we're going to be talking about that today. And once you form that epoxide, there can be an OH group that can attack here, and it's going to be released. So what you're going to have then is and it's gonna, if it attacks here, you're gonna either come from the bottom or this is gonna come from the top. So I'm gonna draw this coming from the bottom. Let me see. It says you only have to draw one enantiomer, so this should work. And you're going to get the other enantiomer too. You don't have to draw it. Or you'll get the other enantiomer if we attack this way. Then this will be on the bottom. Now this will be at the top. So so that should work for question 13. Like I said, it's interesting why they put this question in 12th as far as forming the epoxide. If you've read chapter 13, you'll know that chapter 13 deals a lot with epoxides. And we can do question 14 on the same slide. So it says the best reactant, we're going to put isopropyl chloride. And the best reagent, because why are we putting isopropyl chloride is because, you're making this right here, right? So you need an isopropyl group. So if you have isopropyl chloride, you can insert that magnesium right here. So then your best reagent will be the magnesium, right? Is that it? And then they want the best solvent. We want something non-polar so we don't quench it. So we'll pick diethyl ether. So we'll pick this is non-polar. So that was 14. All right, so we'll go to 15 then. 15, you're making the same thing. It has the same product. It just has two different routes to do it. So route 1, you could pick, I'm just going to draw the phenyl group, my shorthand. You pick this, plus then you'd have your Grignard reagent. And then route 2, you can have this. And then your Grignard reagent would be the magnesium. It would be the phenyl group with the magnesium bromide. And they both give you the product structure on the right-hand side. Is everyone, did this work for everyone else on question 13? I'm just curious. Okay, let me see. Let's just flip how we had the, this is kind of strange. And then we'd have to pick it like that. Oh, I know why it's wrong. I know why it's wrong. Okay, I know why. Does everyone know why this is wrong? I was getting in a little rush right there. Look where the double bond is at. The double bond was right here, right? So I can't draw an epoxide here. I can't draw an epoxide here when it should have been here, right? So the concepts are right. I just, put it in the wrong. I put the epoxide in the wrong place. Try that, and that should work. Did that work? Okay, good. All right, so that was 15. $16 we can put on the same slide. I'll just do this if we need to come over here. They want us to draw curved arrows. So you have that done. Make sure you put the electrons in there. They may want the electrons. I don't know. Does it accept it right if you don't put the electrons? That's a good question. Now we have water. Water is an excellent leaving group so that bromine can come in. For an SN2 type reaction, and it's gone. And we have the alkyl bromide. So we have the alkyl bromide. I'm kind of curious if you don't put the electrons around bromine, if it accepts it as the right answer. We'll put them here. Did anyone else get 15 to work? Let me go back to that one. You know, when I went back to 15, I have a different answer choice now. So 15 looks like it's one of those where you have to it's kind of like an algorithmic problem. I just noticed this on my own. Now I have a different choices. So my 15 choices now. So you have to think about the products that you have. So you may have a different setup than I do. Now I have this set up because my final product is this. So if your final product is not this, before I had a phenol group on it. If your final product is not this, it may not work out. So you have to kind of think, how would you build your final product to get this? Now, if I have that, if this is a carbanion, this can come attack right here. You can see how this group here is right here. Same thing right here. This will come here and this will come here. So you have to kind of think about how your Grignard reagent is going to do, your attacking. So if you have, it depends on what your product is. So if you have that phenol group, kind of think about how you would make that. I shouldn't have erased that phenol one because that would have been the second. I think there's two choices, but I could be wrong. Did that answer choice work for some people now? So kind of depending on what you have will be depending on what the answer that you need to put in there. All right, so we have 15 done, 16 done. So we'll go on to 17 then. There we go. Get rid of that. 17 says the deuterated ethanol shown can be converted to an alkyl halide by a mesylate intermediate. Complete the mechanism, draw the final product, and select the correct absolute stereochemistry of the starting material and the final product. So we have this. Don't forget your lone pairs of electrons here. So that's our step one. So what is the absolute configuration of the deuterated ethanol? It'd be R. And it wants the final product. Oh, let's draw that better. So that's it. It says, what is the absolute configuration of the chloroethane final product? This will be R. You go this way, and then you flip it because the hydrogen in front, so that'd be R. Oh, sorry about that. I got, this should not be R right here, sorry. We're looking at just this right here. You go this way, this would be R, but then you flip it, so this would be S. So this one should have been S. Let's make that big. So that should be it. All right, so any questions so far? All right, we'll go to 18 then. So 18 says a student wants to synthesize the propyl nitrile from ethanol. What reagents would work? You're going to select, there's 1, 2, 3, 4, 5 different options. 1, 2, 3, 4, 5. You're going to select option 2, 3, and 4. Okay, someone has some in the chat. Okay, let me see. This one had HBr in it. This one had PBr3. This one had SOCl. So they're pretty, none of the other options had, these options in there. So you have to look for the ones at HBr, PBr3, and SOCl2. All right, so we'll go to question 19 then. 19 says use two curved arrows to show the fast protonation of the alcohol. So we're going to do a protonation. So you have some type of acid in there. So now we show the dissociation of the leaving group. So that's the dissociation process, plus you get H2O. So now they want you to show the deprotonation of the carbocation intermediate. We have a carbocation right here. So that's our deprotonation. Then we have this as our final product. Let's see. Okay, yeah. Sorry about that. So that arrow, the second arrow should be right here. So the question asked, let me go back to that question. Yeah, so you're protonating this. So I'll get rid of the arrows. So the first arrow, you pronate it, and then this bond will put its electrons on that oxygen right there. All right, you're welcome. So hopefully that works out for everyone. What question am I on? That's 19. So let's see what 20 has in store for us. So go to 20. 20 says indicate whether the reaction involves a CO or OH bond cleavage of the alcohol molecule. which bond is cleaved. The bond that's going to be cleaved is a CO bond. And I'm going to put 21 on the same slide. Remember 21, whenever we have chromic acid, we're going to, and we have some type of group like this, you know, we're going to create the carboxylic acid. So when you have chromic acid, you have to think about that. So we'll do that. We're going to create our carboxylic acid. That's fine. That's fine. That's fine. All right, so it says select the most appropriate reagent for 22. You're going to select PCC. You select PCC because, you know, it's an oxidizer that will oxidize primary alcohols to aldehydes without over-oxidation to the carboxylic acid. So it's going to give you that. It'll give you the aldehyde instead of the carboxylic acid. That's why you select PCC. That's 22. So for 23, we'll do 23 on the same slide. 23, the key to this question is the distillation. You can remove the aldehyde before it turns into carboxylic acid. So that's why you're going to have the carboxyl or the aldehyde product. So you have the aldehyde product right here for 23. All right, so 24 says albuterol is a prescription medication for treating asthma, bronchitis, and symptoms associated with COPD. It functions as a beta-2 androgenic receptor agonist that relaxes the muscles in the airways. As a chemist, you have been consulted on how to convert albuterol to the product. Oxoalbuterol For preclinical trials, select the appropriate reagent from the drop-down list for this transformation. We're selecting the alcohol. That alcohol becomes an aldehyde, and we see that an alcohol becomes a ketone. So we're going to select PCC and DCM, the chloromethane. If you select the chromic acid one, you're going to take that alcohol to the carboxylic acid. We don't want to do that. So that's why we're going to select PCC. Guess we could put 25 on the same slide. It says draw the starting material. You're going to draw this with the alcohol. And then you're going to identify the reagent. You're going to draw with sulfuric acid. That's 25. That's 26 can go on the same slide. There's not much to 26. It says identify the reagent. Well, it's going to be magnesium ether. Then it says it wants to draw the products. We're going to get, the phenol group. Not the phenol group. We're going to get phenyl group with the magnesium bromide. This is going to be your Grignard reagent. Oh, okay. So 26 has more than one part, so I'm going to have to go. I didn't realize that. So we'll continue 26 on the next slide. So 26 part 2. We're going to have formaldehyde. Let me put that down. Formaldehyde and an acid. Reagent 3. So that. I can put 27 on the same slide. So it says in each reaction box, place the best reagent or reactant from the list supplied. So for A, we're going to start with acetone. Then B, we're going to have the sodium borohydride. C will be PBr3. Then D will be magnesium. E will be ethanoic acid or ethanol. So that's what we have then. So ETOOAC is ethyl acetate. Sorry about that. That's 27. And that's it. We're finished. Does anyone have any questions on any of the problems?
Can I stay after class a little bit and share my screen and have you explain a few to me?
Yeah. So I can do that. Okay, so we'll go ahead and take a 15-minute break and we'll continue with chapter 12 then. All right, everyone, let's go ahead and get back to it. So we are on chapter 13 now. We're talking about ethers and epoxides, thiols and sulfides. We'll get to thiols and sulfides at the end of the chapter. It says an ether group includes an oxygen atom that is bonded to two alkyl groups. You can see them right here, R and R. R groups can be alkyl, aryl, or vinyl groups, not acyl groups. This is an ester, not an ether. You can tell it's an ester by this right here. Ethers is a common functional group in many natural and synthetic products, and they give you some examples of some ethers. You can find them in vitamin E, fluoxetine, and morphine. Common names are often used for the ether. You name each R group. So we have ethyl methyl ether. Arrange them alphabetically. So we started with E before M and end the word with ether, and we ended the word with ether. So here we have tert butyl methyl ether. We don't consider the tert as far as the alphabet goes. We start with the B, so B comes before M, so we have tert butyl methyl ether. With the IUPAC name, the larger R group is the parent chain. The smaller R group is the alkoxy substituent. So here we have ethoxypentane. The bond angle in ethers is very similar to what is found in water and alcohols. We can see that the bond angle is 112 versus 109 and 105. So recall, alcohols have relatively high boiling points, and this is due to hydrogen bonding. Remember, hydrogen bonding can occur between this, and this. As ethers can act only as hydrogen bond acceptors. So ethers cannot hydrogen bond amongst themselves. So if you just have two ethers in there, you can't just say, oh, we have some electrons and it's going to hydrogen bond to that methyl group's hydrogen. That's not going to happen. So they give different boiling points. So you can see that ethanol can have hydrogen bonding, has a higher boiling point. And dimethyl ether is somewhere in between ethanol and propane. The larger the ether, the higher the boiling point, and that's due to London dispersion forces. So ethers are common solvents used for organic reactions. They have relatively low boiling points. Oftentimes they're nonpolar. They're easily removed by evaporation, and they are fairly unreactive. The metal atoms with full or partial positive charge are stabilized by ether solvents. Ethers are used as solvents for Grignard because they stabilize a magnesium atom. So if there's a partial positive here, there's a partial negative here, and it can stabilize that. And then the book goes into something called crown ethers, and they've been shown to form especially strong attraction to metal atoms. So you can put some type of metal atom here, and there'll be some type of attraction right there, as we saw. And it's called 12 crown 4 because there's 4 oxygen atoms, 1, 2, 3, 4. And if you count around, if we'll go 1, 2, 3, you have 12 atoms. Likewise, you'll see the same thing with 15 and 18 crown 6. So the numbers in their name refer to the total number of atoms and the number of oxygens. So the size of the metal must match the size of the crown to form a strong attraction. So 18 crown 6 is the ideal size to trap a potassium cation. So you can put a potassium in here and it's trapped, and that's what they're showing there. As metal ions are not soluble in low polarity solvents, the crown ether complexes to the metal cation, the resulting complex is soluble. And it gives you some different examples of where this might be used. It shows you how it's complexing around that potassium cation. Thus, choosing a crown ether depends on the metal cation present in the reaction. Obviously, you wouldn't put the potassium here because it would have a hard time fitting in 12 crown 4. Industrially, diethyl ether is prepared by the acid catalyzed dehydration of ethanol. You can see this is our product, diethyl ether. It's acid catalyzed because we'll regenerate our acid. So we have ethanol. There's a proton transfer, followed by SN2 attack, followed by another proton transfer. This is the Williamson ether synthesis is a viable approach for many asymmetrical ethers. So they show this proton transfer right here, followed by a nucleophilic attack. This would be an SN2. And then we get our product. We get our ether product right here. So that R could be, remember what we talked about, some type of alkyl group. Or it could be a benzyl group. Williamson ether synthesis is a viable approach for many asymmetrical ethers. That means it doesn't have symmetry, right? So this R group, could be CH3, it could be like a propyl group or an ethyl group. That's what they mean by asymmetrical. We wouldn't really want this to be a tert-butyl group because then we wouldn't be able to do an SN2 reaction. So this is consider the two possible routes to synthesize methyl tert-butyl via Williamson ether synthesis. This route will work because it requires a methyl halide. You can see how this will work. This and the bottom route won't work because it requires a tertiary halide. This is recall the oxymercuration demercuration can be used to synthesize alcohols from alkenes. We put that OH group, the alcohol group, on the more substituted side. This is due to Markovnikov regioselectivity for these reagents. All right. So similar alkoxymercuration demercuration can be used to synthesize ethers. So instead of this, if you recall in the previous slide, this was H2O or at an alcohol. Now, if we add some type of ROH group on there, we're going to create our ether right here. And this is also with Markov-Nikov regio selectivity. So you can imagine that, if this R was some type of propyl group, that this would be coming off like that. It says ethers can undergo acid promoted cleavage. So we have a proton transfer here. We have a dimethyl ether. The ether is protonated, generating an oxonium ion. Here's our oxonium ion. A halide functions as a nucleophile and attacks the oxonium ion via an SN2 type reaction, SN2 reaction, ejecting an alcohol as a leaving group. And here we now have a methyl halide. A formation of a second alkyl halide. So we're going to take this, move this down here. The alcohol is protonated again. We have our oxonium ion. A halide functions as a nucleophile and attacks the oxonium ion here, ejecting water as a leaving group. So we have our two methyl halides then. Any questions so far? Says acidic cleavage of ethers to produce an alkyl halide works with HBr and HI. If the R group is tertiary, then cleavage occurs via SN1. Well, then that means it's stepwise. If the R group is aryl or vinyl, substitution doesn't occur at all. Then from chapter 10, it says recall ethers undergo auto-oxidation. So laboratory samples of ether must be frequently tested for the presence of hydroperoxides. And I actually used to make products to test for this when I was at Oklahoma State. I made some type of product that would turn, it was blue and then would turn green upon being reduced, by the organic substitute or product. And if it was turning green, then you knew you had a problem. And this could also absorb some of that stuff too. So the auto-oxidation occurs through a free radical mechanism. I'm going to show the free radical mechanism on the next slide, where you have your initiation, propagation, and finally termination. So remember, this is a homolytic cleavage. So we have our initiation with our hydrogen abstraction. It forms a carbon radical. Then we have our propagation step. then another hydrogen abstraction. And then we go to our coupling step or our termination step. That's shown right here. So it destroys the 2 carbon radicals. So it says recall that the net reaction is the sum of the propagation. So that means if you see it on the left side, if it's on the right side, you can cancel it out. So you have RH, O2, gives off this. This is for cyclic ethers. See, with these cyclic ethers, this is under a lot of ring strain. So you're going to see this undergo reactions. The size of the ring determines the parent name of the molecule. So oxyrane, oxetane, oxolane, and oxane. So it just depends on how many carbons there are. It says oxyranes are also known as epoxides. So an epoxide can have up to 4 R groups. You can see that here, 1, 2, 3, 4. This is ethylene oxide is the simplest epoxide because there's no R groups. There's just 2 carbons right here and everything else is a hydrogen. So although they are unstable, epoxides are found commonly in nature. And once you have the ethylene oxide, you can make ethylene glycol. And ethylene glycol is commonly used as antifreeze. There are 2 methods of naming epoxides. The oxygen is treated as a side group, and the 2 numbers are given as its locants. So we have 2, 3. So at the 2 position, we have 2, 3 epoxy, 3 ethyl. At the 3 position, we have an ethyl group, 2 methyl pentane. This is the same thing right here. Oxyrane is used as the parent name. Recall from this slide right here. That would be the oxyrane. It's just an epoxide. So we have 2,2-diethyl, 3,3-dimethyl oxyrane. So you start your numbering from right here, 1, and then 2, then 3. So that's why you have your 2,2-diethyl. You see your ethyl groups coming here, and you see your 3 position, you have your methyl groups. It says recall that epoxides can be formed when an alkene is treated with a peroxy acid. So we have different conditions to make our epoxides. Metachloroperioxybenzoic acid, or MCPBA. It's in the meta position because this would be ortho, meta, para. So that's why you have the meta. So MCPBA and perioxyacetic acid are most commonly used. The difference is the epoxidation of alkene is stereospecific. So with MCPBA, we're going to get the cis isomer, and then with the MCPBA, we'll get trans here. I guess we'll keep the trans structure right here with MCPBA. Well, let me think about this. Are you still using MCPBA? Cis. Okay, so it keeps the structure. So when you're using MCPBA, it shows that it keeps the structure. Cis will say cis and trans will stay trans. I should say it keeps the integrity. Epoxides can be synthesized from halohydrins. Halohydrins are synthesized from an alkene. And it shows the mechanism on the next slide of how to do this. So a proton transfer. And you can see how we're going to form the epoxide right here. That'll be a good leaving group. So the alkoxide ion functions as a nucleophile and an intramolecular. Intra means within the same molecule. And so the alkoxide ion functions as a nucleophile in an intramolecular SN2 reaction, ejecting the halide as a leaving group. You can see that halide, which is bromine, is a good leaving group. Bromine is large. It's a very good leaving group. We form our epoxide right here. Says note that either route from alkene to epoxide is stereospecific. I think I want to end right here. I think we've had a lot. So we have this cis, using MCPBA, we can generate the same molecule as the reaction conditions down below. So like I said, I'd like to stop right here. So if you have any questions, please feel free to stay behind. I'm going to stop recording. Everyone have a great weekend. Remember, chapter 12 homework is due, I believe it's Saturday. So please make sure to get that done. If you're listening asynchronous, I know there's a lot of you out there, it still is your responsibility to get the homework done. So have a great weekend, and I'll see you on Monday.